Welcome back to the Quad Drone Lab. Today we are diving into one of the toughest problems in autonomous flight. How do you navigate over long distances when GPS is totally off the table?
I mean, it's a huge question, isn't it? Your GPS can get jammed, it can get spoofed, or you could just be flying in a deep urban canyon where there's no signal. In a military context, you have to assume GPS won't be there for you. So how in the world do you build a drone that can fly for hundreds of kilometers and still find its target with absolute pinpoint accuracy?
Well, the secret is a hybrid, multi-stage system. This diagram here really sets the stage perfectly. It compares the old-school WWII dead reckoning approach with our modern three-stage system. We're basically taking a classic, time-tested idea and just supercharging it with modern robotics. This gives us a great roadmap for the whole explainer, a long-range cruise followed by an intelligent, vision-based final approach.
All right, here's our flight plan for today. First, we're going to really unpack the whole GPS denied problem. Then we'll walk through each of our three stages: dead reckoning, terrain referencing, and visual servoing. And finally, we'll pull it all together to show you how the hybrid system works and how you can get your hands on this kind of tech. So yeah, let's kick things off with the big why. Why is it so incredibly critical that we develop navigation systems that don't rely on GPS at all? The simple truth is that GNSS signals are, well, they're fragile. They're pretty weak signals coming from space. They can be jammed on purpose, they can be spoofed to send your drone to the wrong place, or they can just get blocked by buildings or mountains. And if you're talking about military operations, you have to just assume that the enemy is doing everything they can to deny you that signal. It's this exact vulnerability that's pushing us to develop these really resilient, self-contained navigation methods. And that brings us to the very first, the most fundamental layer of our entire system. This is the long-range cruise phase, and it's all powered by something called dead reckoning. So what is dead reckoning? It's really the art of navigating without any help from the outside world. You start at a location you know, and from that exact point, you just continuously track your own motion, your direction, your speed, how much time has passed, to figure out where you are now. You're navigating from the inside out. And I think this comparison is just brilliant. Think about a World War II pilot. They had a map and a compass for direction, a watch to track time, and their own brain to do all the heavy lifting, calculating their position and estimating for wind. Our drone, it does the exact same thing, but it's doing it with silicon. The map and compass become an IMU, an inertial measurement unit. The watch is now a high-precision clock, and all that mental math is handled by something called an extended Kalman filter, or EKF, which is just this amazing algorithm for fusing together a ton of messy sensor data. And for the wind, we have an air data system. It's the same logic, just way more advanced. Let's look at the actual components. So at the very heart of this is a tactical-grade IMU. This thing has gyroscopes and accelerometers that feel every single twist, turn, and acceleration. Then you have an air data system, which is so important because it measures your airspeed. Think about it. Flying at 100 knots into a 20-knot headwind is totally different from flying with a tailwind. All of this data gets poured into our auto-adaptive extended Kalman filter, which acts like this constantly updating probabilistic brain to give us the single best guess of where our drone is and what it's doing. Now, dead reckoning is awesome, but it has one fatal flaw. Even with the absolute best sensors money can buy, tiny measurement errors start to add up. And over a really long flight, this small drift gets bigger and bigger until you have a massive position error. Your drone might think it's over here, when in reality, it's a whole kilometer off course. So, how do we fix that? How do we deal with that massive, unbounded drift? Simple. We let the drone look down. And this brings us to stage 2, terrain-referenced navigation. This is our mid-course correction system, and it is absolutely crucial. TRN is actually a classic technique. It was first developed for cruise missiles, believe it or not. The basic idea is that the drone uses a sensor, could be radar, a camera, whatever, to measure the shape of the ground directly beneath it. Then it tries to match that profile to a digital elevation map that's already stored in its memory. The key here is that it's totally self-contained, no external signals whatsoever. The process itself is often called TERCOM, which stands for Terrain Contour Matching, and it's basically a 4-step loop. First, the drone measures the ground. Second, it searches its internal map for areas that look kinda similar.
Third, a smart correlation algorithm finds the absolute best statistical match. And finally, this is the magic part, it uses that match to get a true position fix, which completely resets all that built-up drift from the IMU. Now this is the modern way of doing it, using vision. Instead of just matching a single line of hills and valleys, the drone can do what's called template matching. It literally takes a picture of the ground, and then it slides that picture across a satellite map in its memory until, click, it finds a perfect match, lining up roads, buildings, forests, you name it. And this is the most important thing to remember about Stage 2. TRN gives us periodic, absolute position fixes. It's the sanity check. It's what keeps the dead reckoning system honest over hundreds of kilometers, making sure our drone actually arrives in the right general area. But, general area isn't good enough for us. For that final kilometer, when we need surgical precision, we switch over to Stage 3, terminal visual servoing. Let me put it this way. Dead reckoning and TRN got you to the right neighborhood. But now, you need to find the specific house, maybe even a specific window on that house. That requires a totally different level of precision.
And this is where AI vision takes over. This diagram here breaks down what we call an image-based visual servoing loop, or IVVS. So the drone's front-facing camera is just streaming video to an onboard AI model, something like YOLO, that's been trained to recognize a very specific target. The model spots the target in the image, calculates the error between the center of the image and the center of that target, and then feeds that error directly to the flight controller to steer the drone. For all of you who like to get your hands dirty with code, let's peek under the hood. This is a bit of Python for the perception side. That first line just runs a camera frame through our YOLO model. The lines after that just pull out the coordinates for the target's bounding box and find its center. Simple, right? But this gives the drone the target's exact location in its field of view. It's the what I see part of the puzzle. And here's the other side of the coin, the control part. This C++ snippet shows how we talk to the flight controller, which in our case is a PX4 running on ROS2. This function's job is to publish a command to the drone. And the really important part is that its parameters, the numbers it sends, are derived directly from that visual error that YOLO just calculated. So you get this incredibly fast, tight loop that's constantly telling the drone, hey, move a little left, now a little up, until that target is perfectly centered. That right there is visual servoing. Okay, so we have looked at all three stages. Now let's put them all together and see how they create this one single, incredibly resilient navigation system. So when you see it all laid out, it's really a chain of escalating precision. The mission kicks off with dead reckoning, which is perfect for covering huge distances, but we know it accumulates error. So every now and then, terrain reference navigation pops in, takes a look at the ground, and just zeroes out that error. Then, for that critical final kilometer, the system switches to high-frequency visual servoing, using AI to lock onto the target for the final approach. You see, each stage beautifully covers the weaknesses of the others. We've gone through a ton of theory today, right? From Kalman filters to YOLO models. But you and I both know the real fun begins when you stop talking theory and start putting it into practice. So if any of this sparked your curiosity today, just imagine what you could actually build. The concepts we talked about here aren't just academic. They are literally the building blocks for the future of autonomous systems. By joining the Quad Drone Lab YouTube membership, you'll get exclusive access to our projects, the full source code, and detailed tutorials that will help you turn these powerful ideas into actual, real-world flying robots. Thanks for watching, and I'll see you in the lab.